Welcome to the first seminar of the semester. So I'd like to introduce today Professor Ranjana Mehta from Texas A&M. She's an associate professor in the Industrial and Systems Engineering Department there, and she's the director of the Neuroengineering Lab. She has a PhD from Virginia Tech in ergonomics, and her lab does research using physiology, biomechanics, neuroscience, psychology, and public health. And she puts all those things together to understand operator behavior, operator stress. She studies in areas including demographics, obesity, aging issues, and she's developing tools to assess operator health and performance in hazardous work. So, Dr. Mehta.
Howdy, everyone. Okay, thank you. I'm contractually required. No, I'm just kidding. I'm not contractually required, but I hope the universe is listening. So thank you all for inviting me to the first seminar. I'm really grateful. We are always very excited to talk about our research, and so I have the next 1 hour. I'm going to keep a track on the clock because I tend to speak a lot, and I want to keep some room at the end for questions. But if there is any burning questions in between, please feel free to let me know, and I'd be happy to have that interactive one-on-one with you all. So as Rob mentioned, my lab is the NeuroErgonomics lab at Texas A&M University, and I do a lot of brain behavior-based research to understand, assess, and to augment human performance and human experiences in safety-critical environments or high-risk environments. Some of those environments include emergency response, offshore oil and gas, to name a few. So these are environments that are sort of characterized by hard to access, highly unstructured, and potentially of high consequence if things go wrong. And the way we look at research in these spaces is through a detailed understanding of mind-motor-machine interplays. And we do that across a lot of different, just understanding human capabilities, but also how humans interface with different automation agents in these environments. So a quick overview of what our lab does. We have a lot of projects. So I spent a lot of time, I bugged Tony a lot about what would folks at Wisconsin be interested in hearing about. And then I decided I wanted to talk more about my research starting from when I was a graduate student up until now that focuses on understanding human fatigue in different environments. So we've done a lot of research on fatigue mechanisms, particularly neuromuscular fatigue mechanisms. We have now since moved on to understanding fatigue mechanisms through a lot of different stressors, so cognitive, extended wakefulness. And then we understand these mechanisms to come up with applications in actual environments. So our students have gone to offshore rigs for several weeks to collect data from offshore workers, quantifying fatigue in these environments so that we can predict future fatigue states. We have done a lot of work around fatigue and understanding how human fatigue changes human-robot interactions and where those vulnerabilities come in and how should robotic designs and human-robot interaction design be developed so that we keep in mind these perturbations that happen in human behavior as they're fatigued. And so the new normal or the new baseline for human behavior needs to be, under states of potential stress or fatigue that is sort of relevant to the environments that we look at, so emergency response and offshore work. We have also started working on developing adaptive interfaces to manage fatigue as well as to train individuals so that they don't get fatigued in the first, or they delay fatigue so that they apply really good strategies to minimize fatigue development. And finally, part of this presentation is going to talk about this new thrust that we have had in the past couple of years on developing closed-loop neurotechnology for work, particularly in emergency response, where we look at when an individual is getting fatigued and then how do we use neurostimulation as a way to delay fatigue impacts. So I started, as I talked about, my dissertation was all about understanding how does mind and motor, capabilities impact worker neuromuscular functions. And all of this was really relevant to me because as a first-year PhD student who knew nothing about human factors and ergonomics, but just knew that I wanted to work with human and systems interacting, I took courses in biomechanics. At the same time, I took human information processing by Dr. Tonya Smith-Jackson, and that really changed what I wanted to do. I really wanted to integrate the neck up and the neck down considerations of humans as they interact with systems, because it is really critical. Like in any environment that you see, we are not just making decisions. We are making decisions as we are walking, running, moving. And similarly, injuries don't just happen because of heavy physical load. It could also happen because maybe you are psychologically stressed, or maybe the psychosocial environment around you, changes how you lift certain objects. And so this mind-motor interplay was really important. And over the years, as I started doing research in this domain across a lot of different groups that I've worked with, it is especially critical when you look at human technology partnerships in high-risk environments. So we have worked with offshore workers, like I said, emergency response, and more recently, we have started looking at human-machine interactions with long-duration space missions. So I did complete a fellowship with NASA recently, where we have learned, some of the gaps that they have around sensory motor functioning that comes up due to ineffective designs around them, whether those designs are based on the training needs, whether they are on habitat design, or it's just processes that they're working on. So some of the early evidence I wanted to just throw it out here that helped us get closer to neuroergonomics investigation was when I did my dissertation, I looked at the impact of cognitive demands or cognitive overload on physical fatigue, localized muscle fatigue. And what we found that cognitive demands, increase fatigability in individuals. They shorten muscle endurance by about 25%. There are a lot of ways in which that could happen. Part of it was cardiovascular demands, or cardiovascular recovery was impacted. We also found increased perceptions of discomfort and pain that could potentially be a mechanism for why physical and cognitive stressors interplay and can impact neuromuscular functioning. And that we found that these effects are task dependent. We did this in very controlled environments, but you can imagine, taking this research outcome and trying to apply this to various settings, and there are a lot of different ways in which cognitive and physical stressors can interact, and they may not, be similar across different domains. So we really needed to parse those out. But what we couldn't understand at that time with traditional human factors and ergonomics measurements or approaches was why this happened. We knew that it happened, and we consistently found these results, but why did this happen? And so that started my journey in understanding mechanisms of fatigue. This is something that my students and I really focus on is we want to document human behavior, but we really want to know why humans behave the way they did. Because once we understand that, we can develop targeted interventions that can help us in getting closer to mitigating the impacts of fatigue. So we knew with neuromuscular fatigue that fatigue is both central and peripheral in nature. So we knew that there are central components to neuromuscular fatigue as well as peripheral components. And we also knew from very separate studies that have been done in the past that there are certain regions of the brain that play a regulatory role in both motor planning, force production, but also in executive functioning or cognitive functioning. And one of those regions were the dorsolateral prefrontal cortex. And so we wanted to know what happens to that region when an individual is stressed using both of these perturbations. But we also, in ergonomics, have traditional central fatigue assessments. Those are twitch interpolation that we do with electrical muscle stimulation. However, those are invasive, although some of my recent work has also become more invasive. But what we couldn't figure out with those techniques is why are those cognitive stressors impacting, fatigue mechanisms? With those measurements, we could know that cognitive stressors result in, lower endurance. But what we didn't know is why that was still happening. So we really needed to, look into the brain to answer that question. I'm an engineer by training. I wasn't a cognitive neuroscientist. I wasn't a neuroscientist, but I was an ergonomist, and neuroergonomics was a field that I found after I graduated with my PhD. And so I really thought when I was doing my PhD research, oh my God, I'm onto something really novel over here. No one's looked into it. And once I became a faculty member, I figured out there's this line of research called NeuroErgonomics by Raja that I wish I had known when I was doing my dissertation. But he was I would say, the central most important reason why I got into this research. And Raja did a lot of work with cognitive neuroscience and looking at brain and behavior at work, but from sort of like a neck-up perspective. So, air traffic control training, what's happening in the brain, how can we infer from that, what sort of, training adaptive mechanisms do individuals follow as they get, as they become an expert. He hadn't done physical ergonomic stuff. So that is where convergence between Raja's expertise and my expertise came in, and he took me under his wing. And so what I wanted to present to you all is what are the sort of insights that we gain from neuroergonomics. So neuroergonomics, like I said, is the study of brain and behavior at work. So it's not just the study of brain, it is how you interact in the environment. So when you look at some of the other physiological measures, let's say heart rate variability, that gives you some really good information on what's happening cardiovascularly to your body, but also how external factors as well as some individual differences can impact you. When you look at the IBI data or even the ECG, raw ECG data that comes from cardiovascular responses, they are one temporally dynamic curve. And it's very difficult to say the change in heart rate is because of A factor versus B factor, especially in cases where you can't separate the two. So you can do that well in a lab environment, but think about an emergency responder wearing a heart rate device and going into the field. I wouldn't know whether the change in their heart rate is because they were that they had an instantaneous stress response, or there was something else that came up that suddenly impacted them. So it's very difficult to parse out some of these constructs that would have been very helpful, because then you can design better interventions to target. When you look at the neural data, it gives you function-specific temporal curves around what's happening in the brain as an individual is experiencing certain environmental changes, right? So first of all, we have multiple of these curves that allow us to deep dive. Second, there are region-specific influences. For example, we do know that there are certain structural and functional segregation in the brain that's responsible for downstream behavior of certain actions. So for example, emotion is regulated in one region, or working memory is regulated by one region, or primary motor contraction is regulated in one region. So we can parse those out, and they have distinct neural signatures, so we can utilize that. But also, when we look at how the brain works, are the different regions working together? So we can look at functional integration and functional segregation aspects of the brain to really look at skills development, to really look at fatigue manifestation. So we can now look at what's happening to an individual's experience over time, not just at any given instant of time. And with that, this is just an example of what we have been able to look into. When we do connectivity analysis of the different regions of the brain, we are able to sort of not just see how over time with fatigue, different networks in the brain reorganize and over time disintegrate, leading to failure behaviorally, but we are also able to parse out individual differences that we have not been able to do so with some of the more traditional performance-based measure. So for example, brain behavior mapping so far in our research has helped us sort of complete the loop between perception, cognition, action, but has also helped us in uncovering individual differences. So we have published several papers where we have found performance outcomes are not sensitive to some to certain changes that we see, particularly between men and women. We have found that performance outcomes are sort of the lagging indicators of what's happening to an individual. And because of that, you lose certain potency of this measure if you want to develop predictive systems, one. And second, you're not able to sort of say whether different groups of individuals are similarly or differently impacted by the conditions that you're measuring. And so when I started looking at some of the measures for neuroergonomic assessment, particularly for motor tasks, because in our studies, we are not just sitting in one place, we are moving, we are having people lift. And in one case, we actually went to the Rellis campus at Texas A&M, where we flew drones and we equipped the individuals with neurophysiological instrumentation to understand cognition in action. When you look at these neuroscience or neuroimaging techniques, we needed something that had a decent spatial resolution, a decent temporal resolution, but is also movable. And what we knew about fMRIs and EEG is that they offered, one or two of these in high resolution, but they were very difficult to implement in highly moving tasks. And so with that, we started working with FNIRS since the 2010 onwards. And we have worked with a lot of different FNIRS devices where we have done a lot of ambulatory work. And this is the system that has really helped us get closer to understanding what's happening in the brain as individuals are experiencing different conditions. So I want to first talk about how neuroergonomics helped us in uncovering certain fatigue mechanisms. If you recollect, I was talking about we found, cognitive stressors reduced endurance by about 25%. And we did follow-up studies with neuroimaging where we didn't find differences in traditional, biomechanical or ergonomic assessments of muscle activity that could give us some mechanistic insights. But when we looked into the brain, we did find that there were dynamic changes that engaged or disengaged certain seed regions of the brain that were responsible for downstream behavior. And that we attributed in one of our first few papers with Raja on these are the seeds of interference when individual is doing a cognitive and a physical task together. And since then, we have been able to sort of parse out for fatiguing protocols across a lot of different muscle sites, how the brain networks reorganize using graph theoretic methods. And we have been able to see how men and women actually adopt different neural strategies. So we have found that men increase in the frontal motor region co-activation, whereas women are not able to. And that can relate to some of the strategies that we can teach when we are developing exercise interventions, but also when we are designing tasks and environments for individuals. More recently, one of my students is finishing up her dissertation on further delving into what's happening as individuals are getting fatigued while they are being cognitively stressed. And not only are we looking into the brain, so we are not just observing what's happening to the brain, but we are also perturbing the brain using transcranial magnetic stimulation to really understand. We see these brain network reorganization when we perturb those regions post-fatigue. Does that indicate loss of neural drive? And if that does, then that is sort of like a causal inference that we can make with neuroimaging and neuromodulation. So we are very excited about the study, and hopefully, you all will be able to read it in the next 1 year when it's up for publication. We started with neuromuscular fatigue, but since then we moved on to different fatigue sources, because when we started doing use-inspired research, we realized it's not just one way an individual is getting fatigued. A lot of times the stressors are not just physical and cognitive, they are also, extended wakefulness. But first we wanted to know what happens when an individual is cognitively fatigued. Does neuroergonomics provide us with similar insights that we have seen in physical fatigue domain? And here we actually found a little bit more, we found more evidence to not rely a lot on performance outcomes. So if you look over here, we had participants come into the lab and they were getting cognitively fatigued for an hour using a 2-back visuospatial task. And we graphed out their performance over time. And we see that the performance is nonlinear. So early they learn how to do the task well, they're learning strategies on how to do the task well, and then over time you see performance decline. When you look at the subjective responses, we see that it sort of linearly increases in them reporting that they're feeling fatigued. When you look at physiological data, heart rate and temporal and spectral measures of heart rate variability, you see that, again, there are some nonlinear trends, but heart rate in general is a pretty decent indicator of cognitive fatigue too. And then we started looking into the brain. So this is activation data from the brain, and these are functional and effective connectivity patterns of the brain. Interestingly, what we found was when we compared the different stages of fatigue development, we found that stages 1 and 2 for brain connectivity analysis to be significantly different from each other, but we only found them different in stages 4 and 5 for the performance indicators. Yes, sir.
I see error bars, so I guess these graphs are averages.
Yes.
Did you separate men and women based on
So yes, in this study we didn't find differences. So then we did a pooled analysis. We always look at first recruiting equal number of men and women, powered enough for each group, and then we put them in statistical model. In this case, they were not different, which was very surprising to us. They are different in the physical fatigue domain, of course. So over here, what we did find was that descriptively, we found that performance is a lagging indicator. And that has implications for, let's say, if you're trying to develop a predictive fatigue model, it's important to know, what's the label that you put there. And it's important to know, what are you really trying to forecast in the future. And I'll talk a bit about that as well. So, like I said, some of the insights that we got from our mechanistic studies was in terms of mechanisms, which we understood a bit more on how individuals are physically versus cognitively fatigued. We also found that even though men and women have similar performance declines, that in some of these stressors, they have different strategies to preserve performance, for them to have comparable performance declines. In terms of measures that we used for fatigue, we found that performance measures are lagging indicators. There is a lot more that's happening. The further you go away from cognition in the brain, the more you have different strategies that each individual adopts to cope with the stressor, right? And so all of that increases the variability that you see in your performance data. And finally, in terms of outcomes, we found that some of the operational performance outcomes are difficult to measure. So we measured, lab-based measurements over here. However, if we were to translate this to the field, we wouldn't get the sort of accuracy, sensitivity, and specificity of, reaction time tasks, and so they are operationally very difficult to gather. What we also found that potentially countermeasures can fill in these performance gaps or these gaps in fatigue, and we can use them to proactively manage fatigue. And that's where some of our other work on using what we learn from mechanisms informs our countermeasures development. So to give you a brief overview, we deal a lot with high risk, hard to access safety critical domains. The challenge is that these are safety critical, they're socio-technical systems, and they are hard to access. Again, I said the same thing. But we need solutions that are user-centered. We want them to be used by individuals. We want these systems, these countermeasures to be effective, of course. We also want these countermeasures to be equitable. We want them to have, similar impacts or similar gains across different groups. We don't just want one group to gain more than another. That creates disparity. We don't want these countermeasures to increase the gaps over there. And we want these countermeasures to be safe. So I'm going to talk a bit about the neurotech at work that we do with TEECS. It's one of our collaborating institutions at A&M that trains about 200,000 emergency responders every year. So we work very closely with them. They have a technology product testing division where we have companies coming in who are creating products and technology for public safety, and they test them. And so we work very closely with these individuals. So we started looking at fatigue in EMS workers. So this is one of our first use-inspired field research that we are starting to look into. When you look at the recommendations that are provided to EMTs, they are told to work shorter shifts, right? So that's great, right? Like only if that would happen. They are told to drink caffeine. Recent studies have come out that have shown, long-term caffeine intake can impact bone health, cardiovascular health, in emergency response groups. So there have been very targeted studies that have looked at this. And they've talked about that there should be reliable fatigue assessments that are done. But when you think about how these recommendations need to be deployed, it's easy to create an infographic like this, but it's very difficult to operate, and it's very difficult to integrate and implement. So that's where I've presented a lot on our work in disaster response, and I've always had first responders come to us and say, do you have a performance enhancement drug that I can use? Because they're just so motivated to respond to an emergency. It's just that they know what happens to them if they continue to go on. And as an example, when we looked at fatigue in first responders as they were responding to Hurricane Harvey, flying UAS for 2 days straight, we found on day 2, their performance on a psychomotor vigilance task corroborated to them being legally drunk in the state of Texas, as if they were that is just day 2 of their mission. And that's how quickly they get fatigued, but they're still, they still want to be there, and they are expected to be there just because they couldn't get restaffed. The roads were closed. No one else could go where they're going, and they needed to provide, road blockage, road closure information to public safety groups that could then, provide the general public with this information. So when you think about designing systems for these operators, you need to understand how fatigued they can get. And any, let's say, HRI design should keep that in mind. We shouldn't design for humans in a relaxed state. We should design for human in the state that they usually are under the context that we are designing that. So we started thinking of why not neurotechnology as a fatigue countermeasure. We know it's out there. There have been several studies that have looked at it, but we didn't know how well accepted it would be. So there is a lot of human readiness level assessment that we needed to do around fatigue countermeasure. Yes? No, that's good.
So you have cognitive stress, and I'm not in this field at all, but you have fatigue, all right? And somehow is fatigue defined as because I sort of view fatigue as an instrument for, like, for example.
Got it. So the way we define fatigue versus stress, right? So fatigue is a function of time. It's time on task across the various stressors that you get. You can instantly stress someone out. You can activate their fight response instantaneously. You cannot instantly fatigue someone. Fatigue, when I say fatigue, it's what the person is feeling. You're right, but the stressor is what is fatiguing them. So the stressor is time, and the stressor is whatever, whether it's a cognitive overload or a physical overload or a combination of these that they're going through. So that's how we differentiate between fatigue and stress, and also, stressor and then fatigue is a strain that is on the individual. So stress-strain relationship between the two. Yes?
This is a follow-up to that. If I feel hyper, maybe with all that,
I think that's the argument we take, in that with performance, you're not just performance data alone. You're not able to say what led to a performance decline, right? So if with caffeine you find the same impact, you need to have some contextual information around to sort of corroborate this decline is probably because of them being in this context for some amount of time. So I want to talk about some neuromodulation tasks. So I'm going to quickly go through it. We thought of neurotechnology as a fatigue countermeasure because, as we found out, we needed to go closer to the source of impairment. In this case, it was, changes in the brain that were happening, because those are much less variable than going through behavioral measures that we needed to change. How we wanted to develop a closed-loop neurotech system. And what we wanted to improve was performance outcome, but I'll talk a bit more about it. So there are a lot of different neuromodulation technologies out there. So you have transcranial magnetic stimulation, transcranial direct current stimulation. That's the one that I'm talking about, TDCS, ultrasound, as well as direct brain stimulation. So we are focused on transcranial direct current stimulation. That's the neuromodulation technique that we focused on. What it does is you send in weak electrical currents. In TDCS, it's direct current. With transcranial alternating current, you send in alternating currents at different parameters of the current. And what it does is you have an anode and you have a cathode. You send in the weak current in the anode. Based on hyperpolarization of the membrane potential, it actually lowers the requirement for the action neuron to fire. And that region now becomes functionally more available to transmit electrical impulses. The challenge with TDCS is a lot of folks call it a snake oil. They say, well, with TDCS you can improve mood. With TDCS you can reduce sleep deprivation declines. And so a lot of different things have been done with TDCS. One of the studies that we first followed when we started thinking in this domain was a study by AFOSR looking at the impact of caffeine versus the impact of weak electrical direct current on sleep deprivation, extended wakefulness. And they did find that both caffeine and TDCS at certain dosage were able to maintain performance with extended wakefulness. But interestingly, with caffeine, you actually see mood decline over time. And with TDCS, you actually saw the preservation of mood levels. And so, again, it's one of those double-edged swords. Is why is it happening? Like, what is the change? Like, where are you finding the gains? And why are you finding the gains? And since then, we've seen an explosion of TDCS research across a lot of different domains. But there are some more targeted understanding of why that change is happening. We are doing concurrent brain imaging and brain stimulation at the same time to understand what those changes are. So we did several studies. This is one of the first few studies that we did in the lab where we fatigued individuals, similar to what I have shown before. This is the cognitive task. It's a manipulation of a two-back test. And we stimulated the frontal region of the brain with 1 milliampere for 10 minutes. The reason we chose these dosages, like I said, we are really interested in understanding the human readiness level of the neurostimulation application in an emergency response. What we have found in prior literature is that people will sit for 20, 30 minutes and they'll get the neurostimulation and then they'll go on to do their extended wakefulness protocols. Emergency responders do not have that. They don't have that much time. They are called. There is a call for EMS to go out, and they need to be within their ambulance in the next 2 minutes. That's how quickly they need to do that. And they are also taking naps in between. So sleep inertia is a big issue in these workers. So we wanted to test dosages that could potentially be operational in emergency response work in the future. So we are first starting to look at the human readiness level. So we tried 10 minutes of 1 milliampere stimulation in the study where we had individuals come in on 3 different days. On one day, they just did the fatiguing task for 60 minutes. It's a controlled session. They weren't wearing the headgear, so they knew they weren't getting any stimulation. We call it the control. The second day they came in, it was all counterbalanced, where they were given a sham, which is a 30-second ramp up, ramp down of 1 milliampere. So they felt something and they thought they got the intervention. And on the third day, they got 10 minutes of the 1 milliampere. And of course, we counterbalanced and everything. Since then, we have done another study which we pre-registered, and it was actually an RCT that we are publishing on right now, where we're just doing sham and high-definition anodal stimulation, which is we are targeting the region that we really want to look at, and we are doing multimodal, brain imaging and electrical stimulation at the same time. So this is what we found. We found that performance was differentially enhanced by the stimulation effect. What I mean by that is, if you look at the red line over there, that's the performance outcome when they were stimulated with the 1 milliampere for 10 minutes. So over time, you could actually see performance improve and actually never go down to the same levels as the anodal, as the control or sham performance decline levels. And that stayed on for 30 minutes. The other thing that I want you to note over here is we actually had our participants come in on previous days to actually get trained on the task, because we do see learning effects, and we wanted to avoid that from happening. When we parsed out these performance outcomes, we saw that in terms of sensitivity, which is they click when they're supposed to, right? So it's response selection characteristic of the task. We found that that also increased as time on task increased, but it was significantly lower for the sham and control group. And more importantly, for response inhibition, which is they didn't click when they weren't supposed to click, and that's a big characteristics for fatigue. We always see declines in response inhibition. We saw that in general performance declined, but we found that for the stimulation group that it was preserved. And we did this for an hour, and we found this initial efficacy that if we just stimulate for 10 minutes, we found the effects to last for the next 30 minutes. And so we were very encouraged by this result, and since then we have tried to focus on a 2-hour task, so we have expanded that 2 milliamperes for 20 minutes, because we want to model dose-response relationships. We can't do an experiment for each dosage level. What we want to do right now is develop a string of studies that can help us in modeling dose-response relationships, where we can say, you know what, if you only have 4 minutes before you have to hop into the ambulance, this is the sort of efficiency, or this is the sort of effectiveness that you will see. Yes, sir. So repeatability. So I think if I'm hearing you right, you are talking about, are there any decay that are impacted by repeatability? Like, are they getting used to it? Are they getting habituated with it? That's a great question. There are several things that we don't know in normal functioning individuals. What are some of these effects? But we do know that there have been several RCTs in clinical populations where we don't see these habituations, where we don't see addiction, or we don't see them wanting this TDCS stimulation over and over again. And there have been some very major studies that have looked at 10 weeks of TDCS every week, or 5-day continuous TDCS, and we have not seen them in clinical population. That doesn't mean that it may not happen here. It's just that gains are they show up differently in different individuals. So that's a great research question that needs to be followed up. More important to how we saw TDCS helping, what we found was that it didn't help in changing their perceptions of fatigue. So the individuals felt, equally tired, like they reported similar levels of fatigue. That's subjective. So they felt the fatigue, it just wasn't relevant in their performance outcome, which was interesting, but also not completely surprising, because we know that, perceptions of fatigue and its manifestation in performance outcomes are very different mechanisms. So this wasn't completely surprising, but it is an important point, because when we design our closed loop system, this is an important consideration for trust. If an individual is given, a TDCS dose, they do expect a change. They may not see that change in operational outcomes, but a lot of people relate to how they feel. And if they don't see that change, it may dissuade them in the future to use it again and again, because they feel that they are not seeing the impact of TDCS. And so this is where, human-centered understanding of how we design these systems need to come in. So when we train individuals on using a system like this, it is important for us to parse out where the gains are happening, why those gains are happening, and where we don't see them, and educating the end users on, you may not see it here, but you can see it here. And then that can probably facilitate technology acceptance. When we looked at, so we did these initial studies in the lab, and we found, performance changes. But we wanted to know, to create a closed loop system, we first want to predict fatigue, future fatigue states. And that future fatigue state then need to say, you need the stimulation right now. So there are a lot of challenges with such system. Once you're fatigued, there is no amount of stimulation that will help you. So you need to target the stimulation before you get to that point, right? So that's another area of research that Dr. McDonald and I were doing with the students' dissertation. And I won't touch more on that, but just enough to understand, HRL, human readiness level understanding. The other thing is, performance are lagging indicators. Self-reports are disruptive, and we saw that in our studies. So what we did is we wanted to know how would such system, closed-loop system, be trustworthy to emergency responders. So we did an ICOR site cohort where we interviewed 60 emergency responders, 1-hour interviews with them, where first we asked them, what does fatigue mean to you? And where do you see its impact on you? And what do you weigh more importantly? Because then that would decide our label for fatigue prediction, right? Because we don't want the performance to decide our labels. We want whatever they feel is important that is declining because of fatigue to define our fatigue states. And so what we found was they didn't care how they felt. They said, it doesn't matter how I feel as long as I'm not making the wrong choices, or as long as I am making the correct choices. I think performance was key for them. So that's when we realized that, okay, so we can go on with performance as one of the ways in which we can predict future fatigue states. And the second thing we wanted to know was, is this even an amenable countermeasure for you? Are you okay with being stimulated in the brain in this region? And if so, in which process in your workflow will this be well integrated? And so they gave us a lot of feedback on, this is what we need to do before we actually hop onto the ambulance, and maybe we could do it there. So we got all of those insights, and we are working on a framework for how to integrate such a potential fatigue countermeasure in this group that is really user-centered in nature. And so what we learned with this study was that individuals, particularly emergency responders, were open to fatigue neurostimulation as a countermeasure, and that 10 to 20 minutes at 1 to 2 milliamperes were effective, and so we want to get more into the dosage level. What we don't have so far is we don't have ecological validity. So we want to see, if we run this through a fire department in their facility, will we see the same responses? We didn't test on emergency responders, the RCT as well as the initial study. We tested it on a college population. So we want to know what happens there and why we find those gains. So we want to explore more on multimodal brain imaging and neuromodulation to understand if we see performance improvements, why that is the case. And decision mechanisms for stimulation is something that we are working on right now, where we need to develop these human-centered algorithms, whether we want to stim or not to stim an individual, that relies on future fatigue states. So we want to forecast future fatigue. But the challenge is, how far ahead can you forecast? Is that sufficient time for you to stimulate? Is that enough time for the stimulation to make an impact? And how long can the stimulation benefits last? So those are questions that we are trying to answer right now. And finally, what is the right sort of appropriate ground truth? Fatigue means so many different things to different individuals. We do know that performance is important for emergency responders, but when we try to develop these models, are there cardiac heuristics we can use for developing these forecasting methods? Are there perceptual responses be good ground truths? Or is there a combination of these that we need to explore? So those are things that we are exploring. I want to stop here. I have half of my slide deck still left. Apparently, I work on Mehta minutes. I've been told they are, times 4 longer than Earth minutes. So I'm going to stop right here. But if you all have any questions for me, I'm happy to talk about some of the other work that we have been doing. But I just wanted to, throw it out over here. I love my lab. They always reach up for the stars and sky and the sun and the moon or whatever it is. But all the work would not have been possible without, the work that my students and the folks in my lab are doing. Thank you so much. Questions? Yes.
So thanks for the talk. It's really
So let me answer the second one first. I think it matters to identify the underlying strategies that individuals take, only because when we do these studies, and these studies get published, when we don't find performance differences, we say there are no differences between sexes. But a lot of times, a lot of these experimental protocols are done in scenarios that potentially doesn't represent the spectrum of experiences that individuals would when these results are being used in occupations. So we study motor control, let's say. Motor fatigue is a perturbation of the central nervous system to understand motor control strategies. Unless we perturb them to those levels, we wouldn't understand how men and women would interact with systems in the workplace, and is one group more vulnerable to injuries than the other. So I do feel that it's important to identify these strategies and say, and see if they're different between sexes, for two reasons. One is what you just said, people learn differently. So there could be interventions that are targeted both in terms of worker training or in terms of just interventions, either in work design, ergonomic work design, or in terms of training. And then two, to actually ask those questions that you did, because we haven't really looked at force control strategies. Is learning on force control strategies different for men or women as they grow over the ages? And then that's we haven't really looked at. What we did is we do make sure that in terms of their initial MVC, that we normalize, which is a standard practice. But we also include their initial MVC as a covariate in our analysis. The reason we do that is in a lot of studies we have found that more than sex difference, initial MVC, even whether or not you normalize the task to the MVC, is a major predictor of changes that you see rather than sex differences. Things like physical activity makes a difference. So for each of our neuromuscular studies, we actually equip individuals for a week with sensors, and we collect physical activity data for a week before they come to the lab, because those are factors that can change your neural drive to your muscles. And we know they make a bigger impact than sex differences. So we try to account for that, but I think your point is well taken in that we have never looked at how, through their lifespan, how boys and girls, how force production and force control strategies are learned. That's very interesting. We haven't. Something to look at. Thank you. Yes, sir.
This is not unrelated to that question.
No, we definitely should report what we share. I think what maybe I should have clarified how I spoke it. So we did a couple of studies on human-robot interactions using visual versus haptic cues, and we found that when I say equitable interventions, if it gets people to the same level, that's great. If the intervention or countermeasure gets people to the same level, that's equitable. But if it disproportionately elevates one group over the other, that's something that we definitely want to report on, with a sort of envelope of saying we want to be cautious about things that that impacts one group more preferentially than other. We definitely want, so with our study with the HRI, we found that women actually under states of stress use the haptic cues to reach to a level of performance comparable to men, and so we found that was an equitable feedback loop for women to get to a level that leveled group performance, like the pooled group performance. So I think, I guess that's.
I'm still puzzled. I mean, if you had an intervention that raised the women above the men,
So I think at that point we talk about personalization, right? Like we talk about what is helping an individual get their best performance. The thing that I'm worried about is we tend to not do our due diligence in evaluating interventions and evaluating countermeasures that look at this. And so it's important that we make sure that our study designs, our protocols, as well as subject inclusion, recruitment, and analysis methods, make sure that we do not overlook this important factor. Maybe that's what I should have said. Thank you for the clarification. Yes, sir.
So great talk, and that last conversation made me think about seatbelts. And because of that, a lot of women have died. So I think adapting it to the characteristics is important. The question I have. Yawn, other people
Yeah.
yawn. And I'm curious if you thought about how that social component of the treatment might come.
We haven't, but we did look, for a proposal that we were considering to write, we were looking at how incident response can get, how we can use sort of department-based fatigue assessment based on, where they are distributed and where the incidents are happening. But in terms of manifestation of fatigue, that's a very interesting point. We haven't really looked into it. With offshore workers, we did find that they would, when we asked them questions about do you report if you see, have you ever reported if you see one of your coworkers being fatigued, but they're still continuing to do the task, because at any given point on a rig, you have one of each individual for each shift. There is no replacement. And so we've asked them this question is, do you tell them to go sleep, and a lot of them, there is the psychosocial component. It's just not, we've never studied it in terms of fatigue manifestation, but we have studied in terms of safety culture. We are studying right now in terms of safety culture is what would, if I identify another person as fatigued, how would that change what I do, how I compensate for that individuals, or what sort of safety decisions I make when I see that happen. But that's a very interesting point. The yawning thing definitely is a very interesting point. Oh, I'm so sorry I couldn't present some of the other stuff. That is also, but I'm happy to share these slides if you all want to review it. And if you all have any questions, I'm happy to take them. My email address is right there. It's rmehta@tamu.edu. Thank you so much.